So in this video we are going to discuss the recurrence relation of dearrangement. So what is basically dearrangement? That is, suppose you have numbers like a1, a2 dot 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 till an. So you have n numbers and now you are taking a permutation of them. So like let's say b1, b2 dot 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 till bn. Okay, now the question is that how many permutations are possible. That is, suppose you have n distinct numbers, so n factorial permutations are possible, right? So now if the question is asked like how many such permutations are possible such that here none of the ai's will be equal to the bi's, okay? So for each I, the ai won't be equal to the bi. So then in how many ways, how many such permutations are possible? Or in other words, like you can think like this, that is, suppose there are n houses and the postman wants to post their letters, like those n houses have their corresponding letters and those letters are with the postman. Now the question is like in how many ways the postman can post all the letters to the wrong address, okay? So that's basically the dearrangement. So now if you know so what we are doing is we are denoting the dearrangement of n distinct objects as dn, okay? So now this recurrence relation, so we are going to prove it. Now you know, all of you who have gone through dearrangement have learned dearrangement in your counting class, in your while you have learned counting. So basically you know that it has a nice formula, okay? So if you use that formula and we can prove the LHS is equals to RHS, but that's a very that's not how we are going to do it, and that's not a very clever way to do it as well. So a clever way would be to give an argument, okay? So anyone can do that, LHS equals RHS. So we are not interested in that, okay? So we are going to prove it with the help of an argument, okay? So now what we'll do is we'll take that problem, that is, let's say suppose we have n houses, okay? So house 1, house 2 dot 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 till house n, okay? So we have n houses, so this is suppose house 3 and dot 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 so on till house n. So we have n houses and the postman is having n letters, and the letters to the corresponding houses, and now the postman will post all the letters like in the wrong address, okay? So now try to think like this, that is, what we'll do is we'll fix one house, okay? So it doesn't matter whether it's h1 or h2, so we will fix one of the house, okay? h1, h2, h3, anyone. So without loss of generality, let's fix h1, okay? So we fix this house. Now what happens is that why did we fix it? So we are going to watch like where the postman is posting the letter L1. So suppose the house 1, the corresponding letter, let's say it's L1, L2, and then house 3 it's L3, and house N is Ln, okay? Now the letter L1 won't go to house 1 because the postman would post it in the wrong address. So now we are going to watch where this L1 is going, okay? And from there we are going to make some observation. So first, where this L1 is going, it has n minus 1 options or n minus 1 choices, okay? Because from 2 to n, anywhere it can go. Now wherever it's going, okay, so what we are going to do is like we are going to now look at the letter of that house. So suppose for example this L1 is going to house 3. So now we are going to look at where L3 will be going. The letter 3 will be getting posted, okay? So here there are, we'll mainly divided into two cases. That is, L1 can go to H1, okay? So basically the letters of H1 and L3 can go to H1. So basically the letters of this house 1 and house 3, they are getting exchanged. Or if the letter L1 is going to the ith house, so the ith house letter and house 1 letter, they are getting exchanged. This is one possibility, okay? This is one case. The other case is that like it won't go to so letter L3 or let's say the ith house letter, so that letter won't go to H1. Okay, so these are the two cases, right? So now case 1, okay, that is I have like chosen my like the house 1. I have fixed my house, okay, house 1, so its letter is going to the ith house. So let's say that so instead of taking 3, so let's say that we have some ith house. So I is ranging from 2 to n, okay, so it's going to the ith house, and the letter Li is going to H1, okay. So then what happens is that these two letters are getting exchanged, and now you are left with n minus 2 houses, okay. So that can be dearranged in dn minus 1 dn minus 2 ways, because I have n minus 2 houses and their corresponding letters, and that I can dearrange, or the postman can post all the letters in the wrong address in dn minus 2 ways, okay. So this is the case. Now the other case is that in case 1 the ith letter went to house 1, so the other possibility is that it won't go to house 1, okay. So these are the two cases which are exhaustive in nature. So case 2, that is now try to imagine the scenario, what is happening actually. So sorry. So here I have my letter L1 which went to some ith house, okay, and in the first case that letter Li went to house 1. Now in the second case I'm saying that the other possibility is that it won't go to house 1, okay. So then I have to think what then how in how many ways the rearrangement can happen. So if it doesn't go to house 1, so now try to think that okay, the ith house has got its letter, okay, so letter L1 has been posted to the ith house, okay. So now I am deleting that ith house from the picture, so I delete, because L1 has been the letter L1 has been posted to house the ith house. Now I'm the postman, suppose, and I have letters like Li and also like L2, L3 and whatever, like the rest of the houses, okay. So Ln, okay. Now see, I have basically this n minus 1 houses and their letters, and in such a way that is now in this case Li won't be going to house 1, L2 won't be going to house 2, L3 won't be going to house 3, and so on. So now try to understand that it's basically the a dearrangement scenario where basically I have like n letters, n minus 1 letters, and their they won't go to their corresponding houses. So basically like here Li is being treated as L1 which won't go to house 1, right? So that's why like this can be done, and like first our L1 has n minus 1 choices again, okay. So I has n minus 1 choices. Now whichever I is whatever be that ith house, so its corresponding letter won't go to house 1, okay. So and I being the postman, I can see that like I have n minus 1 houses and I have n minus 1 letters, such that Li won't go to house 1, L2 won't go to house 2, L3 won't go to house 3, and so on. So I can see that I have to dearrange these n minus 1 letters, so that I can do it in dn minus 1 ways, okay. And now since that exhausts all the possibilities for dn, so now I can write it as dn minus 1 times n minus 1 times dn minus 1 plus dn minus 2, and so that's the proof of the recurrence relation. And now the next thing is that let's say that here the second part, that is we have to show that dn is even if n is odd, okay. So now you can very well understand that if n is odd, we have proved the recurrence relation here. So this part is going, I mean, first of all, dn is an integer. You're counting the number of ways in which you can dearrange n distinct objects. So that's an integer. So this part is an integer, and multiplied with n minus 1, which is like, since n is odd, so n minus 1 will be even. So then dn becomes even if n is odd, and that's the proof for this problem. So I hope you have enjoyed it, and if you have learned something, so don't forget to put a like. And yeah, thanks for watching, and keep learning and keep watching, and see you in the next one.